Morning, everyone. Thanks for coming to the seminar today. It's a great pleasure to have Professor Lihua Jin from UCLA visiting us today. Professor Jin received a PhD from Harvard in 2014 with Professor Su, a giant in the field of mechanics and materials. And then she did a postdoc at Stanford with Professor Chen as a giant in the field of stretchable electronics. Okay. So Professor Jin's work focuses on mechanics and soft materials, stimuli in quantum materials, instability, fracture, soft robotics, biomechanics, a whole range of emerging topics. Professor Jin received a number of awards, and nothing to go through all of them, but some of Extreme Mechanics Later Young Investigator Award and the NSF Career Award in 2021. If I have to apologize, I have to leave in the middle of the
no problem.
Because one of my PhDs schedule at 10:30. That's the only time for all the PhDs, for all the committee members. So I apologize for that. She's going to talk about software materials for software machines. So let's give a warm welcome.
Thank you for the invitation and nice introduction. So today I'm going to talk about soft materials for soft machines. So what I'm first showing you here is a soft machine in nature. What you see is an octopus, and it can significantly deform its own body and squeeze in and out of a narrow bottle. And once it gets out of the bottle, it sends the background color. You see it can further change the texture and color of its own body to camouflage and protect itself. So the reason octopus can change the color is because there are bags of segment underneath its skin. Using the muscle to pull those bags, it can change the color. So as you see, soft machines in nature are highly deformable and functional. Next, I'm also showing you some synthetic soft machines. The first example is a very soft and flexible pneumatic soft gripper that can handle a very fragile jellyfish. So the second example you are seeing here is a photo-actuated liquid crystal elastomer thin film. And you shine light from left to right, and from left to right again unidirectionally. You shine light, you can see it can deform sequentially and move unidirectionally. So the third example I'm showing you at the bottom here is an electrically driven swimming soft robot. And it can swim in deep sea. As you see, all those synthetic soft machines, they may not be as agile as the soft machine in nature, but they are deformable and trying to achieve functions. So the advantage of soft machines are their capability of handling fragile objects, safely interacting with human beings, and because they have low modulus, they can potential for biomedical devices and therapeutics. However, there are also a lot of challenges in the field. So stimuli-responsive material can significantly change their shape or volume in response to external stimuli. They are widely used for different soft machines. Typically, they can change from one configuration to another configuration through kinetic processes, such as reaction, diffusion, and viscoelastic relaxation. By understanding those kinetic processes, you can not only control their response speed, but also the kinetics governs how they can evolve spatial-temporally from one configuration to another configuration. But it's challenging to predict and control the spatial-temporal response of those stimuli-responsive materials. Being able to do this, you can achieve new technologies such as 4D printing and also self-folding origamis. So this work is produced by the group of Michael Dickey and Jan Genser's group at this campus. So a second challenge is for soft materials, they have to undergo large deformation, but sometimes the material tend to be fragile and can be easily broken. So the second challenge is how can we design and fabricate soft materials with superior mechanical property, especially fracture properties. Third of all, it's also challenging to design and manufacture soft structures for programmable functionalities. So here I'm showing you some functionality like locomotion, manipulation, and shape morphing. And this is work done by Professor Jie Ying's group. That's a very nice work here. So therefore, there are lots of challenges. So in my group, Mechanics of Soft Material Lab, so I'm working on different aspects. So first of all, we are working on stimuli-responsive material. Some topics including motive physics, constitutive behavior of those material. They're controlling their spatial-temporal responses, and some specific topics including stress order coupling of liquid crystal elastomer and the phase separation of hydrogels. Then our second topic focus is on general mechanics of material, particularly large deformation of soft material, fracture, and mechanical instabilities. By understanding those fundamentals, we further try to achieve functions, and we want to make soft machines and mechanical matter materials. Specifically, we work on shape morphing, soft robots, and also reusable energy absorbing materials. So today I'm going to focus on a few topics. First of all, I will show you spatial temporal control of soft materials and how we can use that to achieve local motion of soft robots. Then I'm going to talk about very special material, liquid crystal elastomer, how their stress order coupling behavior can lead to very unique fracture property. Finally, I'm going to talk about a new type of mechanical instability and how we can harness that for application such as reusable energy absorbing. Yeah, let me start with spatial temporal response. So hydrogel is a polymer dispersed in solvent, and they show both solid-like behavior because they are long polymer network cross-linked by covalent bonds. But on the other hand, they also show liquid-like behavior because the solvent can transport in and out of the polymer network. So daily life example of soft material, soft hydrogels include jello we eat, contact lens, diapers, and soft tissues. So hydrogel can significantly change its volume in response to a range of stimuli, such as pH, temperature, light, electrical, and magnetic field. So you see how significant the volume change can be. And hydrogels can also be used for applications such as soft robot and drug delivery. So this work is also done by Professor Olin Valev's group here at NC State. So here we are interested in some type of photoresponsive hydrogel, so which means when you shine light, So there are nanoparticles in the gel which can absorb light and convert it to heat. Then the heat can change the hydrophobicity of the hydrogel, make it hydrophobic, and can expel water out of it. So now if I shine light locally at some location of the hydrogel, and I can create a temperature gradient, and the water can diffuse out, but it takes time. Therefore, it can also create some gradient of concentration within the hydrogel. So the interesting behavior we discover is if you have a hydrogel cantilever beam, and I have a light fixed from the side, we actually observe self-excited oscillation. So you have a light, then the hydrogel can oscillate by itself, and for a very, very long time. And more interestingly, we observe. So on the left case, you see the amplitude actually start from a high value and decrease. But what's on the right is start from a low value and actually can increase. But for both cases, after a long time, the amplitude saturate and become a stable oscillation. So we want to understand this system. First of all, what is governing this self-excited oscillation? Then you must have energy pumping to the system. And what is energy flow within the system so that it can maintain this oscillation? So with those questions in mind, we started to do some model. Yeah, and here the experiment is in collaboration with Professor Ximing He at UCLA. So then we built a simple model. So we first consider hydrogel undergo equilibrium swelling. Then we superimpose a small deflection of the hydrogel with respect to the equilibrium state, described by this oscillation equation. W is a deflection, and the first term describes inertia, second term describes damping, third term describes elasticity. So the unique thing is on the right-hand side, it describes a photo-induced moment. So that's because I have a light locally on one side, but not on the other side. Therefore, I can create a water concentration. Equivalently, it can create a photo bending, photo moment. So which is a term on the right-hand side. In order to determine the spontaneous photo moment, so we need to solve a diffusion equation across the thickness and to determine the concentration gradient, and therefore we can know what is the photo moment. Combining these two equations together with the boundary condition, we describe when on the side you have light, the chemical potential is considered as be negative, but on the other side without light, the chemical potential is considered as 0. So combining this equation and boundary condition, we can solve its motion. Specifically, there are multiple time scales in this problem. So one time scale is the inertial time, and another time scale is the diffusion. By solving this equation, indeed, we can observe this kind of self-excited oscillation. But now let's zoom in to one half period and look at the behavior. So this describes the deflection. So this half period means the beam is just going down, therefore going downwards. Therefore, the light is on the top surface. Correspondingly, this describes the effective photo moment. So at the beginning of this half period, so the photo moment is negative. But once the light is on the top surface, it can create a gradient. So the top surface, the hydrogel shrink, but the bottom surface is still stays swollen. Therefore, it can create a positive photo moment. Therefore, as you see, the photo moment start to, from the minimum value, start to increase. By the end of this half period, the photo moment gets to the maximum value. So we can further plot the bending angle and also calculate the energy. So within this half period, the energy decrease but then increase. Eventually, it creates a net positive work done into the system. So that's why you are pumping energy into the system. So this is because you see there is a phase difference. So that tells us that you need to pump photomechanical energy into the system at the right timing such that you can really pump energy into the system. So this is like when you push a swing or you jump on a trampoline, you need to do work at the right time. This is because the diffusion has some delay which creates this phase difference. Then moreover, we found that the time difference, the time scale for the diffusion and inertia also have to be comparable. such that you can really pump energy into the system. So from our model, we can also tell the amplitude sometimes can increase, sometimes can decrease if you tune material property and tune geometry. So next, we further study, we do a scaling analysis for the energy, try to understand the energy. We found that the energy positive work done to the system is proportional to the amplitude, but the energy dissipated in the system is proportional to the amplitude squared. Therefore, by equating this to, here we conduct this scaling analysis, show this really is the case. By equating this to energy, so that can give us the stable amplitude, so which is supposed to be the stable amplitude eventually. Then by comparing the initial amplitude with a stable amplitude, we can determine a phase diagram which governs amplitude increase region and amplitude decrease region with respect all the dimensionless numbers in the system. Then you want to ask, how can we make use of this self-excited oscillation? So working with Professor Ximing He, so we actually develop a swimming hydrogel soft robot. You just fix the light and the soft robot can actually swim away from the light. So besides hydrogel, we actually can control and predict spatial temporal responses in a variety of other stimuli responsive as well, stimuli responsive materials. So another example I'm showing you here is a shape memory polymer. So shape memory polymer is a cross-linked polymer. So you have those cross-links in the system, but they have a glass transition temperature, Tg, above the room temperature. Therefore, at room temperature, it's in the glassy state, so it's very stiff. But then you can heat it up so that now the temperature is above Tg, the material is in the rubbery state, then you can easily stretch it. Now, next, you can easily stretch it, but then next step, you cool it down. You cool the temperature down again, but with the mechanical stress still applied. Then, because now the material goes back to the glassy state, then you can fix the shape, even after you remove the load, then you can fix the shape. But whenever you heat the material to the temperature above Tg, it can recover its original shape. This is so-called shape memory effect. So we are interested in the kinetic response of this recovery step. And particularly here, we are considering some photothermal shape memory polymer. So when you shine light, you can generate heat. And typically, there's also a light intensity decay in the thickness direction, which will create a temperature gradient. Then you can also have thermal conduction, and you also have some thermal loss on the boundary. So moreover, when the temperature at a specific location is above Tg, the material can undergo viscoelastic relaxation. So assuming if you originally pre-stretch the material, then whenever the temperature is above Tg, it can relax the state and shrink back to its original shape. Therefore, due to the temperature gradient, maybe the top surface will recover, will shrink back first, while the bottom surface is still elongated. Then you can create a bending. But when you shine light for longer time, such that the temperature everywhere is above Tg, the shape can further recover. So therefore, you expect a bending and then unbending process, even if you fix the light. So indeed, by simulation experiment, we can show this process. You uniformly shine light, and you can see the material can undergo this bending and unbending process. And more interestingly, you can deform the material into an inhomogeneous state. For example, here you have a thin film of shape memory polymer, and we can indent it to deform into some specific shape. Now, what if we shine light not uniformly everywhere, but more towards the left end? Please imagine what you will expect the deformation and motion. So what do you see here? Because we shine light more towards the left, therefore the left side bend early. Then it can trigger the flipping over of the material, and on the other hand, now this right side start to bend. And eventually, because everywhere the temperature goes above Tg, therefore it can eventually completely relax. So as you see here, the whole process is governed by kinetics. And we are not changing the environment at all, but it can undergo this complex motion. So next, I'm showing you one more example, autonomous motion of humidity-driven polymer. So the setup is also very simple. So we have a polymer thin film, which is humidity responsive. And there are many thin film like this, even like a nylon film. You can purchase and put it into a humidity chamber. And then you set the top humidity is low and the bottom humidity is high. Then people observe robust and interesting behavior. You see this polymer thin film can bend. And moreover, by tuning the geometry or the relative humidity, you can see a range of motion. So the second type, they call it oscillation. And the film can just oscillate back and forth. And the third type, they call it locomotion. Though the film can bend and completely flip over and move around crazily. And this phenomenon is robust, and it's observed in multiple literature. So therefore, when I first saw this, it blew up my mind, what's going on, like how to understand. So if you have a thin film, on the top and bottom, the humidity difference is very, very small. And what is causing the bending? And moreover, this crazy motion. So I didn't understand what's going on until we analyzed this carefully. So we realized the key thing is actually, so the film is deforming, therefore they deform to different location. But on the other hand, because the film, although the water can diffuse through the film, but it's very slow. Therefore, essentially, it's an impermeable film, right, in short term. Therefore, the film itself is changing the humidity distribution as well. Then let's see some simulation we have obtained. So in the first cases, we obtained this reconfiguration. And in the second case, we indeed observe this crazy oscillation. And those are the observation in this phase diagram when we change different region of the phase diagram, when we change relative humidity, film size, and some material diffusion time scale versus diffusion time scale in the chamber. So the third behavior is this flipping over. So by this, this is a simulation in COMSOL. We combine solid mechanics and dilute species together. We need to use this arbitrary Euler-Lagrange configuration because it's sort of like a coupling solid and liquid together. But the key point we learn is, so it's really this coupling effect. First of all, you are deforming the film to different position in the chamber. But on the other hand, the film is sort of impermeable. It can also move the liquid around. Therefore, this coupling effect gives rise to this very interesting and complex autonomous motion. So to summarize this first part, we show that indeed we are able to predict and control those spatial temporal behavior of stimuli-responsive material. And we show this coupling kinetics and inertia can induce phase-driven self-excited oscillation, and heat transfer and viscoelastic relaxation govern the complex motion of shape memory polymers. And the coupling between film displacement and evolution of water concentration leads to autonomous motion of humidity-driven, humidity-responsive polymers. So next, let me switch the gear to talk about liquid crystal elastomer. So liquid crystal elastomer is a very special elastomer combining liquid crystal property and elastomer. So for liquid crystal are typically composed of rigid rods and align certain direction in this so-called pneumatic phase. But on the other hand, if you heat up this material, it can undergo a phase transition from this pneumatic state to the randomly oriented isotropic state. So on the other hand, elastomer is a lightly cross-linked polymer. Now, if you embed those liquid crystal polymers either on the main chain or the side chain of the polymer network, you form this liquid crystal elastomer. So under low temperature, those liquid crystal rods align in certain direction, and they can distort the polymer network into this ellipsoidal shape. So this specific direction is called director. But once you heat up this material, it can undergo the phase transition. Now the rods become randomly oriented, then it can relax the polymer network back to the spherical shape. So therefore, it can induce a large macroscopic shape change. So typically, this shape change can be larger than 100% once you just heat a sample. And moreover, this process is reversible. Once you cool it back, it can recover its original shape. So therefore, liquid crystal can produce high work density, are typically considered a very ideal artificial muscle for soft machines. Liquid crystal elastomers have very unique mechanical property. Most interesting thing is their stress and order coupling behavior. So if you have a liquid crystal elastomer with a director aligned in certain direction, but now if you apply an external force, which is non-parallel to the orientation, you can actually rotate those director towards the stretching direction, and which can give rise to a large spontaneous strain. And because of this reason, they show anisotropic property. If you stretch liquid crystal elastomer in the parallel or perpendicular direction, you see very different stress strain curve. And moreover, they also show high rate dependency. This is the viscoelastic property. So what we are interested in is the crack tip behavior. So if you have liquid crystal elastomer with such unique behavior, the stress and the director orientation can couple together, then we ask the question, what if at the crack tip, so you have high stress concentration and very highly inhomogeneous stress field. So what will happen to the direct field and how that will further change the deformation and the fracture behavior of liquid crystal elastomer? So our methodology here is we combine computation and also the experiments to study this. So particularly we use finite element to study the crack tip field, and we also use digital imaging correlation, DIC, to capture the whole strain field, and we use transmission circular polariscopy, TCP, to capture the director field. So let me first tell you a little bit more of our methodology before I move on to showing you the results of crack tip behavior. So here we fabricate liquid crystal elastomer following the literature to synthesize monodomain MAE chain liquid crystal elastomers through a so-called two-step cross-linking process. Then in the sample, in the film, we fabricate the director aligned in certain direction, but we can cut the sample into long strip or different shapes in different angle with respect to the director. Then here I'm first testing some homogeneous behavior, therefore I'm uniaxially stretch the material. Let me first show you the result of TCP. We use TCP to capture the direct orientation, especially how that is evolving while you are stretching the material. So mainly we have two cross polarizer, and depending on the angle of the director, you can either see a dark field when the director is either parallel or perpendicular to the polarizer, or you can see a bright field when it is in 45 degrees with respect to the director. So what I'm showing you here is the TCP result. Yeah, then by measuring this line intensity, we not only obtain this stress-strain relation, but also we can capture how the director is evolving with respect to the external strain. Here I'm further showing you some results for different theta angle. So the theta naught means the angle of the director in the initial state with respect to the stretching direction. So therefore, in the first case, it's essentially parallel to the stretching direction. But in the later case, it's ordinarily in the tilted direction with respect to the stretching. So as you see, the stress-strain behavior looks very different. So that is mainly because for the 0 degree case, the director doesn't rotate at all. But for 30 degree and 60 degree, the director can rotate while you increase the external strain. So that's why this can lead to the different stress-strain curve, because the rotation of the director can further give rise to a large spontaneous strain. So therefore, with increases of the initial theta angle, you can see a higher strain that you can achieve and with a lower stress due to this spontaneous strain. Then moreover, we also see highly rate dependency, not only for this previous reported stress strain curve, but also for this microscopic director rotation. So when you stretch it very fast, we observe a delay of the director rotation. Then next, we also want to use the DIC method to capture the entire stress field, a strain field in the material. And in particular, the interesting thing is even you are doing only uniaxial loading, because the director is rotating, so therefore you expect a large shear strain in the material. So that's why you see that initially the shape is rectangular, but after deformation it becomes parallelogram. So that's because of the large shear strain due to the direct rotation. So I'm further summarizing our result here. First of all, we compare the result from DIC for the stretch in the stretching direction. For different loading rate, indeed, it should expect to be equal to whatever you apply externally. Then moreover, we observe this large shear strain for all those different tilted cases. And those shear strain are also rate dependent. So next, I'm further going to tell you a little bit of the model we are using later for the finite element. So this is a relative well-accepted model. So you can see the textbook or more papers for more detail, but we are mainly adopting this model. So we describe the free energy of the liquid crystal elastomer by the following components. First of all, the first term is this new classical model. Mainly it's describing the liquid crystal behavior. Then the second term is called the semi-soft term, describing the non-ideality of the liquid crystal elastomer. Then the last term is so-called Frank energy. It is describing the gradient of the director. So therefore, different from other typical polymer, now the total free energy is a function of deformation gradient, but also a function of the director. N is the director. It becomes a free variable which can change around, right? So then by minimizing the energy or using the energy conservation, we can derive two governing equations. As we can expect it, because now we have two variables. So the first equation is still as usual. It's the stress balance of the Cauchy stress. But now, because we also have another variable director, then we also have a second governing equation which governs the evolution of the director. And by the way, here we are not considering any viscoelastic effect, but right now we are further working on that. Okay, now we have all the tools. We are ready to look at the results of liquid crystal elastomer and the crack tip. So we are considering a liquid crystal elastomer with an edge crack of length A. Now we apply external displacement or external strain to pull the material. And we are looking, we assume the crack doesn't propagate, but we are looking at the field in front of the crack tip. So in the final element, we consider a rounded crack, but we need to make sure the mesh is refined enough to capture the crack tip field. Then we are using DIC and TCP to observe the field in the material. So first of all, what I'm showing you here is for the case when, here I'm defining another angle alpha. So alpha is a complementary angle of theta, which is describing the orientation of the director. But now this alpha angle is with respect to the x-axis. So first of all, when alpha equals 90 degrees, which means the director is along the stretching direction. So 90 degrees with respect to the axis. So therefore, it's along the stretching direction. Then let's look at the video here. This is describing the director change as a function of strain at 3 different locations, at 0 degree, 45 degree, and negative 45 degree. Yeah, let's look at the result here. So with respect to the strain, so the director at a different location are rotating differently. So essentially what this is telling us is on the top half of the surface, top half of the sample, the director rotated counterclockwise. But at the bottom half, the Dirac rotating clockwise. So they are rotating, and eventually they want to align together with the surface of your crack tip. So can be also further seen here by the distribution of the Dirac angle with respect to this circumferential phi angle. So on the right-hand side, I'm further plotting the principal strain distribution with respect to this phi angle and also principal stress. Essentially, we are studying this stress concentration. So what we observe is the stress concentration is still occur at the center point, but strain concentration occurs at a location deviating from the center point. And actually, we observe two spots of strain concentration. So that's mainly because the Dirac, at the crack tip, the Dirac is rotating. Therefore, you observe this unusual strain concentration behavior. So next, let's also look at the, I'm comparing the results from the finite elements for the direct field with that obtained experimentally from the TCP method. You see they agree well. And here I'm also showing you the U2. U2 is a displacement in the y direction, comparing finite elements with the DIC method, and they also agree well with each other. So next, I'm showing you the result when the Dirac is in the 60 degree. So therefore, you have a liquid crystal elastic film, and the Dirac is in this tilted direction, 60 degree with respect to the x-axis, and we are stretching in this 90 degree. So let me show you the result here. So again, I'm plotting the direct evolution as a function of strain for 3 different initial phi angle for corresponding to the 3 points here. So what the result is telling us is that we actually observe a domain wall. A domain wall here. On the left-hand side of the domain, the Dirac rotating clockwise, and on the right-hand side of the domain, the Dirac rotating counterclockwise. So on the right-hand side, I'm also showing you the strain and the stress distribution at the crack tip for the principal strain and principal stress. And you see neither of them have stress concentration at the center, but deviate from the center, showing this non-usual behavior. So it's easy to understand because you have the Dirac in this tilted direction and they're rotating around. So again, I'm showing you the result from finite elements and from the TCP, comparing the Dirac field. Indeed, from the TCP, we also observe this domain wall. At the bottom, I'm showing you the result from finite elements and the DIC for the displacement field. So you see the displacement field is highly isometric with respect to the crack plane. So finally, I'm also showing you the crack opening plotted on the left-hand side for the different initial Dirac angle and comparing with a new hooking material. As you can see, they are very different. For initial angle, alpha equals 90 degree, which means parallel to the stretching direction. The crack opening is much larger compared to other cases. So that's because your Dirac do not rotate a lot. Therefore, the material itself is stiff, and you have to open the crack a little bit more. But in other cases, the Dirac themselves can rotate, give rise to the displacement. Therefore, you don't need to open the crack too much. Then on the right-hand side, I'm further calculating the J integral, which means how much energy is released when you have a crack increase per area. So when we calculate the J integral, we can find that because the free energy is different from other typical rubber, we have an extra term because of Dirac rotation. But if you reorganize this form, the final form we obtain is still similar to a typical J integral for a rubber material because the material anyway, it's elastic, right? Hyperelastic material. There's no energy dissipation. Therefore, the J integral can still recover the typical form. And indeed, consistent with the crack opening, we observe when you have larger alpha knot angle, the J integral is higher, which means there's more energy to be relaxed in the material when the crack is propagating. You have a large driving force for the crack propagation. So let me also summarize this part. So I'm talking about the liquid crystal behavior. They show highly coupled stress order fields. So the director of liquid crystal elastomers can rotate towards a principal stress direction. And we also observe this highly rate-dependent stress director rotation and the shear strain. And more interestingly, we study this crack tip field. We observe significant and highly inhomogeneous direct rotation at the crack tip. And the crack tip fields of liquid crystal elastomers are very different from those traditional rubbers. But we are actually just at the very beginning of studying crack behavior of liquid crystal elastomers. Now we are further studying those viscoelastic effects, and moreover, we want to study how the crack will propagate probably through a complex path within the material, and moreover, their fatigue behavior. So now let me spend the last few minutes to talk about some other applications of soft materials. So far, I'm mainly discussing stimuli-responsive material. So if you want to tune their behavior, you have to go through sophisticated synthesis. So therefore, it's typically hard to tune their properties. But on the other hand, there are this emerging idea of mechanical matter materials, so which means materials with microstructures, which can give rise to very unusual mechanical properties. For example, one example showing on the left is multi-stable matter material showing multi-stabilities. So when you load the material, they can stay in certain stable state, even when you remove the load. So the second example I'm showing you on the right-hand side is a matter material that can twist when you apply a compression. So therefore, microstructures can give rise to unusual mechanical properties. And those fabrication of those materials are significantly benefited from additive manufacturing. And because their properties are more or less governed by the geometry, therefore there is a vast design space to tuning the different properties of mechanical matter materials. Or sometimes people also call them architected materials. So here we want to harness mechanical instability recently discovered in our group for applications. So as you know, if you have a beam, if you have a high aspect ratio or a low width to length ratio, so this WL ratio here means the width to length ratio. If you have this low width to length ratio for this beam subjected to axial loading, axial compression, you should expect Euler buckling. So which means after the buckling point, the force will slightly increase with respect to the displacement. This is a traditional Euler buckling. But now if you increase the width to length ratio, so you actually observe this so-called snap-through buckling, which means after the buckling point, the force will decrease with a further increase of displacement. But recently we discovered that if you further increase the width to length ratio, which means a very wide beam, we observe this snapping back buckling, which means after the buckling point, if you follow the equilibrium curve, both the force and displacement actually decrease, but with the slope still remain positive. So we want to make a use of this snapping back behavior. We foreseeing that it can achieve energy dissipation in a self-recoverable manner. So for traditional energy absorbing material are typically based on plastic deformation or fracture. Therefore, you can achieve high energy dissipation, but in a non-reversible manner, right? So you are destroying the material. Therefore, they can be used only once. We are interested in developing reusable energy absorbing materials. So one way here is the mechanism is through this snapping back instability. So how energy is dissipated here? So if you follow this force displacement curve, load material up to this A1 point, and they will snap to this A2 point. Correspondingly, there's also a snap in the energy landscape. While when you unload the material, it will first go back to the A3 point, then snap back to the A4 point, also corresponding to a snap on the energy landscape. And the loading and the unloading do not overlap, but forming a hysteresis between them. So which indicates energy can be dissipated through this loading and unloading process. And moreover, because once you unload, the material can completely recover and the deformation can be completely elastic. Therefore, we would further expect ray-independent behavior. So with this idea in mind, we fabricate this energy-absorbing material. So the main idea is here we form these multi-layer structures. In each layer, there are an array of wide columns. So how we fabricate them? We use 3D printing together with sacrificial molding. So we first 3D print this structure composed of PLA and water-soluble PVA. Then we pull the pre-cured silicone elastomer and cure the elastomer. Then we dissolve the water-soluble PVA and eventually obtain this freestanding structure. Then we further add these hinges so that we can achieve the deformation mode we want. Yeah, but on the other hand, please also note that those wide beam structures are all internally connected such that we don't have a high requirement of adhesion between different layers to ensure the deformation. Here I'm showing you the behavior of this metal material during loading and unloading. So during loading, you observe 8 peaks correspondingly to the buckling of these 8-layer structures. And you also see a long force plateau, which means force mitigation in this material. Then during unloading, again, you see 8 peaks corresponding to unloading of these 8 layers. And the loading and unloading curve do not overlap, but there's a hysteresis indicating the energy dissipation through this process. And once you unload the material, it immediately recovers its original shape, so which means it's reusable and self-recoverable. We further want to use some theory to help us to understand and predict this behavior. So as an input, we have the force displacement curve for a single column. So for these 2 cases corresponding to the snap-back and snap-through cases. So now we have this multi-layer structure. We assume it's connecting in series of a chain of columns. So because we assume they are connecting in series, therefore the external force equals to the force in each of the column, but the external displacement equals the summation of the displacement of all the layers. Then for a given column, under given force, there are 3 corresponding displacements. Then now I have n columns. I need to do this combinational problem, right? For each column, it can in the 3 different possible states. Therefore, I can plot all the possible displacement and obtain many branches of these curves. But not all of them are stable. And I need to further study the Hessian matrix to study which branches are stable, which are indicated by this solid curve, and other branches are unstable, indicated by this dashed curve. Then if I further connecting those neighboring stable curves, I can obtain this loading and unloading curve. Here I'm showing you the result for the different number of layers and for the different width to length ratio corresponding to the snapback and snap through cases. And the area, shaded area, corresponds to the amount of energy dissipation. So what we can see here, the snapping through case dissipates more energy under the same n and grows faster with n, so it's more desirable. And on this page, I'm showing you the experimental result previously we measured, compared with the theory we predicted here. And note that there is not a single fitting parameter. There's not a single fitting parameter. And I would say the agreement is still pretty well. So you see a little bit difference. So that's because in experiments, due to defects in the material, therefore typically the critical force for buckling would be reduced. Here I'm further showing you a dynamic test. So we are dropping this material from top with some heavy load on the top. So therefore, there's an impact at the bottom. Then we measure the force on the top and plotting here with respect to the energy input. So as you can see, in a wider range of energy input, the force reaches a plateau indicating force mitigation. And moreover, from the video, you see not a lot of rebouncing of the material indicating energy dissipation. And moreover, this force we measured here is comparable to the peak force we measure for the static case, which indicates rate-independent behavior in a wider range of loading rates. And moreover, this is an architected material or mechanical matter material. So their property is governed by geometry. I can tune the aspect ratio such that I can significantly reduce the energy dissipation. And moreover, if I apply a preload, at the bottom case, I apply a preload, I can also shift the peak force. And moreover, in this case, I also change its stability. So you observe when I load it, different layers buckles, but when I unload it, it actually becomes bistable. It can lock in the deformed state, even when you remove the load. So this is one idea, right? Making use of snapping back instability for energy dissipation. Next, I'm going to briefly talk about a second idea. So the main question is, what kind of energy mechanism can dissipate energy but do not cause damage of the material? So therefore, the second mechanism we are harnessing here is through friction. So we are making this so-called programmable granular matter material composed. We have a few different designs, but the main idea is composed of this granular material together with some elastic components, elastic bands and strings, such that the relative motion of those granular material can dissipate energy, but the elastic components can maintain the integrity. Once you unload the material, they can recover its original shape. And here I'm only showing you some quick demonstration. On the right-hand side is our matter material, and on the left-hand side is the material already after this deformation as a control. So we have a suspended glass sheet here. And once you have an impact, on the left-hand side, you see the glass complete scatter. On the right-hand side, because the matter material is dissipating energy, and the glass still stays intact. So if you pay attention to one of our results as an input energy, actually so far, those reusable materials are only capable of dissipating energy at a very, very low level, orders of magnitude lower compared to the traditional non-reusable energy absorbing material. So therefore, our current efforts and future directions to further increase the energy dissipation absorption capacity by integrating, dissipating from different mechanisms, material, mechanical instability, and friction. So actually, I don't have too much time to talk about the second literature here, but we have already designed some matter material which shows reusable energy absorption capacity on the similar level as those traditional non-reusable ones. So therefore, let me wrap up my talk. Here, I'm mainly showing you three aspects. Hopefully, those three aspects are trying to address the three challenges I talked about in the beginning. So I'm showing you how we can predict and control the spatial temporal behavior of stimuli-responsive materials to achieve autonomous motion. And I'm also studying the special liquid crystal elastomer and understanding their fracture behavior. And potentially in the future, by understanding their fracture behavior, we want to design liquid crystal and other soft material with superior mechanical properties. And finally, I'm also showing you how we can design mechanical matter materials to achieve programmable functions. Hopefully, in the near future, we can combine all those different aspects to achieve next generation soft materials. So with that, I would like to thank all the group member, collaborators, funding supports, and thank you for your attention.
So So, question?
I had a question on the liquid elastomers. In our lab, we had some trouble doing DIC on large deformation polymers because the paint cracks, the speckle coating paint cracks earlier than the polymer it's coating. But on, I think it was your slide 29, you showed a video where there was a large deformation. I think it was in tension. And I was wondering if you did anything specific or special to make sure that the speckles stayed on the material without cracking.
Yeah, we actually didn't have too much issue of the cracking. We are mainly painting some inks. So therefore, what's remain on the particle are local nanoparticles, like carbon particles. I think there's not a lot of other material to bridge in those particles. So therefore, we don't have significant cracking problems. Yeah. Yeah, so for this hydrogel, actually you see those videos, those are real time. So the frequency typically is around 1 hertz. Yeah, 1 hertz. So yeah, here you can also see it's around 1 hertz. So I would say, first of all, for hydrogel, the time scale is typically long because it requires diffusion. But then for this one, because you don't require diffusion through the entire thickness, but mainly on the surface, and moreover, in this material, we indeed have some way to speed up its diffusivity. So therefore, it's already, I would say, it's relatively fast compared to other available hydrogels.
And so that was going to be my follow-up question. How can you tune the frequency? Is it the mechanical properties of the hydrogel?
Yeah, so if you want to achieve diffusion in hydrogel, then you have to create large pores. Large pores, then that can speed up diffusion. Then on the other hand, so this will sacrifice the mechanical property. But people also have some other way so that if you locally achieve some freeze drying, you have crystallinity or some glassy components, then you can locally strengthen the material so that you can still balance the time scale versus the mechanical property. Thank you.
More questions on this? Yeah, I got a quick question actually for the last part about the magnitude for energy absorption. So you have shown, right, so you can tune the oil buckler with the carbon, right, so different aspect ratio. And then, so my question actually is related to the, say we have energy absorption, in terms of the energy absorption divided by the density, I would say the energy absorption density, so that means the energy divided by the mass of your materials, right? So because the mass is also important in that case. So in your case, I don't know, if you compare this density with other materials, how gonna be, is gonna be great, or I don't know, how gonna be scaled?
Yes, yeah, we did this. So yeah, actually I didn't show you, but that's mainly in our the second reference we listed there. Yeah, let me first show you this number. It's actually a little bit embarrassing. So this number is fairly low. So if you're familiar with this field, then this number, right, a few Joule, this is relatively low. But to give you some sense, for helmet, football helmet, typically you require 10 Joule for the energy absorption. And this we can achieve with this material because we use a relatively soft material. If we increase the modulus, then we can achieve the energy required for helmet, but it's very far away from if you have a car, right, collision. But in this paper, yeah, our recent paper, I didn't have time to talk about, but we really, I would say for the number on that slide I show you, this is like 3 or 4 magnitude lower than what is needed for compared to traditional material. But in this paper, we indeed increase that number to that level. So mainly how we achieve it, mainly friction here, this is a very low density, but you want to increase the area for friction, then you can potentially increase the number. And moreover, if you combine the different mechanisms together, you can also increase the number.
So here the friction actually play a more important roles, right, to dissipate the energy
Yes.
compared to this snapping with additive absorption, right?
Right, so this is a different design. So in our previous design, it's purely through this. So this is purely through buckling. But this is a completely different design. It's a different design. So this is completely by friction. Yeah, but presumably later we can also combine them together.
Great, thank you.
Thank you.
Any other question from the audience? Okay. Yeah, if there are no more questions, let's turn off speak again. Thank you.
Thank you.
Great. Recording.